Okay, we are ready to start. Good morning once again. This is the second session of the day. We have Roland Yu from Sophos Australian lab talking about Android, what's new with the Android packers. Roland?
Yeah, thanks. Welcome to the presentation. Okay, I'm Roland Yu. I'm going to talk about the Android packer. So in the last few years, SophosLabs has discovered the explosive of Android malware, and we recorded over 1 million Android malware. Most of them is coming in the beginning of 2014. Also, we have seen the evolution of technology used in Android malware, including repackaged legitimate application with malicious code, using obfuscation tools such as DexGuard and ProGuard, hiding functionality into binary file, append malicious data to other file like PNG, or using the junk code or files. So today I'm going to present another advanced technology, Android packer. So we all know what is packer in general. So packers are programs that are used to compress and encrypt the executable file without affecting the execution semantics. So as we know, Java is the programming language used to develop an Android application. But we didn't heard about any Java packer. On the other hand, we have seen the rise of Android packer. So this probably because 3 reasons. So Android is able to convert multiple classes into a single DEX file. And it support to use a native binary. Also, we have seen the Android operating system is getting more and more popular. So what is Android packer? So Android packer have capability of encrypting original DEX file, decrypt it in the memory at runtime, and execute via DexclassLoader, DexclassLoader. So the rest of presentation consists of 2 parts. The first part will provide a deeper insight into Android packer. We will give a comparison between the obfuscation tool and the packer, introduce several popular packing services and their features. Also, in the last 1 year, SophosLabs has recorded more and more Android packed malware. I will show it in a graphic. So the last one in this part, we will talk about the working principle of Android packing service. So in the second part, first I will present challenges to existing reverse engineering tools and the dynamic system when we diagnosing the malware threats. Afterwards, I will develop a solution to overcome these challenges. The developer is based on a plug-in of the Volatility project for analyzing malware. I will demonstrate its result for a packed sample. So in summary, I will discuss the generic detection for packed malware, and finally, I will talk about the trend of Android malware in the future. So first of all, it's necessary to understand the difference between the obfuscation tool and the packer. So the popular example of obfuscation tools are ProGuard and DexGuard. So let's take a look at the obfuscation tool. So the tools will investigate files in an APK file, especially the Android manifest XML and class.dex. So for the XML, it will obfuscate like the name of services, receivers, intent, and activities, just like Anna and Jack's slice. And we're using some optimization for the binary XML file. For the class.dex, it will encrypt strings classes at tempo detection code and using the Java reflection. It also is insert some Django code to stop the compiler from Dex to jar, bug smiley, IDA. Then in the step 3, it will combine the modified class.dex and modify the XML file, then build a new APK. So on the other side, the packer will also investigate this file, including the XML and class.dex. It will configure the XML file to make sure that the unpack component will be loaded initially, and it will encrypt the original DEX file and replace to somewhere, especially in the access folder. And it will replace a completely new DEX file with load functionality to load that unpack component. The unpack component is usually based on the native binary and put it into the lib folder. So they will integrate all these components and build a new APK. So we can conclude that the main difference between the obfuscation tool and the packer is that the packer will add a completely new DEX file with functionality of execute the component and load the original DEX file in the memory. So let me introduce some popular packing service provider: APK Protector, Banco, and iJarMe. So APK Protector claims they are the first company to provide protection for Android, while Banco and iJarMe are both from China. So all three packing service provider works perfectly for the Android version 2.1 to 4.3. Just because the binary file works very well since version 2.1. And since 4.4, Google is transferring from the Dalvik architecture to Arctic architecture. And they were originally created for protect against repackage issues in loss of intellectual property. They are trying to stop evil things, but create another evil things. So they based on online service and including the technical like anti-tempo, anti-decompiler, and anti-debug. Furthermore, Banco employs several antivirus scanners to prevent malware being packed. However, the scanner engine from Banco are not able to accomplish its malware-free functionality. So this graphic shows the trend line of Android malware based on three packers. So since September 2013, there is a dramatic increase of malicious sample packed by Banco. So on the other hand, we have seen the utilization of APK and iJarMe has a continuous and steady growth of malware during the last 7 months. So all the packing services are based on online black box systems. So developers upload their application and get packed one without knowing any knowledge of their inner work. So for malware analysts, it is vitally important to know their inner work, as we need to analyzing payloads of packed malware and offer a suitable solution. So to make the reserve engineering simple, I create a test application to upload to three service providers and get the packed one. So the test application contains the main component of Android, such as activity, service, broadcast receiver, and with a native binary. So I will investigate the difference in terms of dynamic and static. So this table records the edit file in the packed APKs. So you can see the APK protector only add a binary file. Banco is insert several digital files in the metadata directory and encrypt the original DEX file into the Banco_class.jar. It also insert several information collecting plugins. So Banco support both x86 and ARM architecture by using the different native library. So iJarMe is fairly simple. They just encrypt the original DEX file to the iJarMe.data and only support ARM architecture. So the second table displays the modified or replaced file in the packed APK. So APK protector only modified the original DEX file, while Banco and iJarMe reconfigure the XML file and and replace with a completely new class.dex. So let's take a look at the code tree of decompiled class.dex for each of them. So when we investigate this graphic, we can conclude that APK protector is not an Android packing service, but an obfuscation and jungle code injection tool. It will encrypt the sensitive strings by using the AES algorithm and in this APK protector 2 classes. So on the other hand, both Banco and iJami provide complete backing service. So Banco equips a group of standard standard classes and also show the encapsulated services, broadcast receivers, and content provider from the original class.dex. So iJami take a further step. It will replace with its own classes, native application and super application. So several issues, technical issues, need to be addressed to understand the processing, unpacking processing of iJami. The first one is how to make sure that unpack component to be executed initially. So the key point is the application class. So as the context of the entire application, the application class will be the starting point when executing the program. So you can provide your own implementation by specifying the class name in the Android manifest application tag. So in our case, it's the com shell superclass. This is the start point. The second point is where and how to unpack original Dex file and how to dynamically load the unpack one. So in iJami, a library exec using the D-in-INIT to implement above functionality. It also including the functionality like check the signature and the integrity of the encrypted Dex. They're using the library exec main to call the D-in-INIT and start the load and the run functionality in the DexClassLoader layer. So iJami is able to stop runtime anti-debugging by modifying the Dex header in the memory. So the modification is from the beginning of the Dex file to the 28 bytes in hexadecimal number. So as a result, it can stop anti-debugger to tracing the original Dex file in memory by just searching the Dex magic number. So it also brings the inconvenience for the Volatility project in part 2. So Banco using the same technology, application class, to make sure load the code dynamically, load the code in the first stage. But Banco is complicated than iJami. So the starting point is the application wrap-up class. So it's using the util class to implementation the main functionality in the application layer or direct layer, while the A core class will implement a functionality in the library layer. So let's jump to the util class. So you can see it including functionality of check the integrity of class.jar, check system if the system is x86 or ARM, then copy related library, encrypt the class jar and the genuine binary to specific folder, and create a child process, and then call the myClassLoader. So the A core class of Banco dealing with binary, such as the library seg.exe in the library of Android. So however, it is impossible to establish a relationship between the Java source code with the library code, because all the functionality in the native library are encrypted. So the normal standard format should be like Java underscore, package name, class name, and method name, like this way. So when we run the Banco packet application, it will create 3 processes instead of only 1 in the original one. So these 3 processes in the Banco are doing the p-trace to each other, so that debugging tools like GDB have trouble to connect any of these processes. This is because in the Android, p-trace will limit to only 1 process to observe and examine the trace's memory and register. So these 2 figures shows the evidence about the multiple tracing in 3 Banco's processes. So we just give an overview of technicals in both Banco and iJami. They are using the integrated checking to make sure the class is anti-tampered. They will encrypt the original Dex file to make sure that decompiler tools failed. And it's difficult to establish a relationship between the between the Java source code and the library code. And both of them using the 2 different technicals to block analysis from debugging tools. So let's jump to part 2. The first one, firstly, I'd like to describe some challenges due to the above packing service. So challenge 1 is existing reverse engineering tools are not competent to disassemble packed application due to the anti-decompiler characteristics. So the payload of packed malware are encrypted by advanced cryptography such as AES and DES. And the packing process and the key generation are classified as confidential by these companies. The algorithm, the decryption algorithm are embedded in binary file to make reverse engineering much more difficult. So challenge 2, a dynamic system like Joybox, iGenSign.com cannot offer successful dynamic results for packed application. So this system either provide very basic static information or just crash when we're trying to start application. The challenge 3, as we know, Android packers present 2 runtime anti-debugger technicals. iJami is able to modify the Dex header to stop memory searching, while Banco using the anti-p-trace technology by creating the interaction processes. So this has caused a serious consequence for existing debugging tools, such as GDB, gcall, memory searching, even for the volatility projector. So challenge 4, so by using an Android packer, criminals is able to change a Dex file completely as a way of avoiding signature-based scanner. So even if the antivirus has a database that including the signature of the original APK file, it will not be able to detect the newly packed one with the same malware. Therefore, we develop a plugin based on Volatility project to overcome these challenges. So the solution will be based on 3 segments. The segment 1 will outline required environment and steps for the memory acquisition. So in order to perform memory analysis, a copy of RAM from targeted Android device or emulator is required. So since Android is based on Linux, a newly developed loadable kernel mode named Lime is used for memory acquisition. So it's necessary to cross-compile Lime to use on the Android device or emulator. So this step is set for the cross-compile, set for the the source code and compile kernel mode and compile Lime and dump to the memory. You can find these steps from online Wikipedia. I have a reference in my white paper. So in segment 2, I will concentrate on the volatility framework and expand the new plugin for analyzing acquired memory and locate offset of unpacked DEX in the memory map. So Volatility project is a single comprehensive framework for the memory analyzing of Windows, Linux, Mac, and Android system. It holds outstanding features such as open source, Python-based, extensive and scalable API. It pre-ships with a lot of useful plugins for Android, including the Linux PS list, Linux Pro map, dump map. All these plugins are used in the next parts, in the next slides. So, as I talked several times in the part 1, since the DEX header will be modified by iJAME, so we use the map list structure as an alternative to search the original DEX file. So these two tables describe the structure of a DEX file in different format. So the header item is located in the beginning of a DEX file, and this map list located in the middle or end of the DEX file. So let's take a look at the header item. It starts with magic number, checksum, blah, 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 blah. And the number 8 is map offset, which you can use to jump here. And the total size is 70 bytes in hexadecimal number. So when we jump to here, it starts with the number of item, then the type head item, this ID should be 0. Then the size actually is not size count, it must be 1. Offset is 0, it's just like here. And followed by the string ID item, then offset must be 70 because this length is 70. Then followed by the 0 to 2. So we're using these findings to assign a specific searching in the Yara rule. So in the volatility, each plugin is able to call another one. So additionally, the result from one plugin can be provided for further processing in other plugins. So a plugin usually consists of a class name and 3 standard functions: init, calculate, rent, text. The first functionality, init, is the constructor of the class object with capability of calling the super class constructor and define the command line option. So in our case, the class name is APK underscore packer find DEX. And in init, we define a parameter PID, a short option is P, and some description. So here is the searching string I talked about in the previous slides. So the calculator function loads address space, accesses, and pass data, then prepared outputs. So the first, it will initiate a Yara rule search. Then it will get a map list from specific PID. So the list contains the memory region and the access permission of the stacks heaps dynamic linked library. Then we start a loop. I think somewhere we start a loop here to read the mapping, to read the data from the anonymous mapping, because the unpacked DEX file should be in one of them. Then we're using the Yara rules. We're using the Yara rules to locate the offset of the mapping list. So once we got this map list, we will continue searching to get the type map ID and map list offset. Then we're using the yield to generate outputs. These outputs are including the task ID, virtual memory address, offset of DEX header, and the map list offset. So the last function, rental text, will accept outputs and print data on the screen in the standard fashion. So in segment 3, I will demonstrate the usage of volatility plugins to locate the offset of unpacked DEX and write a selected memory, map to disk, and patch DEX header if required. So this step is for the memory acquisition. So with using the emulate with customized kernel, then we push the Lime into the Android device. In the meantime, we'll just install the application, packet application, and start it. Then we're using the Lime to extract the memory, make sure the memories exist. Then we're using the FLS and icat to copy the file by node number. Then we're using after we dump the memory, we can examine the file with the Volatility plugin. So first we will find the PID by using the Linux PS list. For the Banco one, we just focus the top one because this is the main one. And once we find it, once we got the PID, we can use it in our new plugin to get the task ID, virtual memory start and end offset, and the DEX head offset and map list offset. In step 3, we will using the dump map to write a memory region to the file. Then we will truncate that file to get the original DEX file. So I use the single quote around the original just because the Banco will insert their monitoring code in the original DEX file before packing. So for the iJami DEX file, it is hard to restore the first 28 bytes in the head section. But you can just pack the first 7 bytes, then DexGuard and BugSmart can decompile it. So we provide a practice and a successful solution to acquire the original DEX file from packed application. However, developing an efficient and effective detection solution for this packed malware is a complicated task because it is impossible to unpack a packed malware and detect the payload in the runtime. So based on the background and the information in part 1, I think the generic detection might be based on the combination of the Android manifest file, the size of the encrypted payload, resource files, and some specific file like resource AIC. So in summary, this paper provides an overview of several more popular Android packers, such as Banco, iJami. I demonstrate their working principle in terms of dynamic and static analysis. And they have some very particular characteristics, such as DEX header modification, as well as anti-p-trace technology from Banco. So afterwards, I discussed several challenges, such as the explosive of Android malware, packed malware, the inefficiency of existing reverse engineering tools, the failure of dynamic systems, and the obstruction of generic detection. So therefore, we offer a solution based on the Volatility project. Actually, it's a framework for the memory extraction and the investigation. So it supplies plenty of plugins. However, we have to develop a customized plugin to explore the process map list and locate the offset of the original DEX file. I also demonstrated it in a packed sample. So in the future, I display here by an image file. So we all know what it is. It's obfuscations plus packer, and we know what it's doing. But the problem is how can we detect it? How can we extract the payload when we analyze it, when we want to detect it? So that's it, question and answer.